Good morning. Today we'll be talking about linearized 2D supersonic potential flow. In a previous module, we looked at subsonic, even incompressible potential flow. We said that potential flow can be modeled using a number of building blocks such as sources, sinks, ODCs, and free stream. Then we made small disturbance assumptions and we developed something called a thin airfoil theory. Then we got very useful information such as the lift curve slope is 2 pi, aerodynamic center is at the quadricard, and so forth. Now we turn our attention to 2D supersonic potential flow, where none of those assumptions will work because now we are in a completely new speed regime, which is the supersonic flow speed regime. So let's take a look at what's going on. We are again going to make the same assumption. We are using a thin airfoil. In supersonic flow, the airfoils will be extremely thin, not even 12%. It would be more like 4 to 6%. The thinner the better because of the very strong shock waves that form otherwise and the very high wave drag that you get. Also, we assume that the camber is mild. Many supersonic airfoils do not even have any camber, because camber, as we'll see, does not add anything to lift. It only adds a lot to the drag. Again, we assume that the angle of attack is very small. It's not even 5 degrees. It's more like 1 or 2 degrees, maybe 3 degrees. That's because the dynamic pressure at supersonic flow is so high, you do not need a large CL to produce the lift that you need. We also assume that the leading edge is sharp, so that any shock wave that forms in the vicinity of the leading edge is attached to the leading edge. So we don't have a blunt, separated, detached shock wave upstream of the nose of the airfoil. Therefore, we do not have a subsonic region. So the entire flow is supersonic. We have already developed the governing equations. We have linearized potential flow equation shown here, except now the Mach number is greater than 1. Therefore, rather than square root of 1 minus m infinity squared as being defined as beta, like we did in subsonic flow, you will have to flip the sign and say square root of m infinity squared minus 1. This is a positive number. We will call that lambda. So when you flip the sign here, this will also become a minus. So the governing equation becomes like this. Xx simply means the second derivative with respect to x, second derivative with respect to y. The surface pressure distribution is shown in here and also the boundary condition. Again, we apply the boundary condition now at the xy plane rather than at the actual body surface. This is a reasonable assumption because the airfoil is very, very thin, camber is very small, angle of attack is very small. So here is the governing equation. So the person who looked at this equation for supersonic flow, he's called Ackeret, A-C-K-E-R-E-T. He started as follows. He said, I'm going to assume a solution of the form phi as a function of x and y could be thought of as a function of a single variable c, where c is a combination of x and y as shown in here. You could later on see that this is a straight line. The slope of this straight line is dy over dx equal to 1 over lambda. 1 over lambda is 1 over square root of m infinity squared minus 1, which works out to be the Mach line. Therefore, these are nothing, c equal to constant is a Mach line. So Ackeret was assuming that the phi was constant along Mach lines. Let's see how good this assumed solution works. So we have to take a second derivative of phi with respect to x. So let's take the first derivative. d phi dx is, we are taking the x derivative of phi. We could think of it as a c derivative of f, which is an ordinary derivative, times the partial derivative of c with respect to x. Since c is given in here, c with respect to x is just 1. Therefore, d phi dx is df dx. Now, the second derivative can similarly be done. d by dx of d phi dx. d phi dx is df dx. d by dx is d by dx times dx dx. So you just get a second derivative because this is 1. By a very similar process, d phi dy and d squared phi dy squared may be computed. So when you plug in this expression for d squared phi dy squared here, and then this expression lambda squared times this expression here, we notice that they cancel, so the governing equation is indeed satisfied. Therefore, this is a pretty good equation. So Ackeret's assumption that phi is a constant along a Mach line is pretty valid. You may remember that in expansion fans we mentioned that along expansion fans, density is constant, pressure is constant, temperature is constant, Mach number is constant, and Prandtl-Meyer function is constant. So in linearized flow, instead of an expansion fan, we just have Mach lines. So along Mach lines, the phi is a constant. Likewise, if you now look at this function a little bit closely, this is a straight line. C equal to constant means x minus lambda y equal to constant. The slope will be 1 over square root of m infinity squared minus 1. These are Mach lines. They are straight lines. They have a constant slope. So in the case of an expansion fan, the fan slope keeps changing based on the local Mach number. Here we have everything based on the free stream Mach number. So if you plot these Mach lines on an upper surface of an airfoil, for example, you'll get basically straight lines that are parallel to each other. All of them will have a Mach angle based on the free stream Mach number. So tangent of mu infinity would be 1 over square root of m infinity squared minus 1. These Mach lines are parallel to each other. They do not fan out or expand as do the Prandtl-Meyer expansion waves that we saw earlier. Now let's look at another solution. This is for the lower surface. Again, we are assuming phi of xy to be another function called g, where g is a function of eta, and eta is a function of this. Again, this is a straight line. This one has got a slope dy over dx equal to minus of 1 over lambda. That's a negative slope. Again, we can go through the motion, take the second derivative of phi with respect to x, plug it in here. Second derivative of phi with respect to aay, plug it in. This is the expression, plug it in here. Then we will get everything will go to 0. So this is also a very good solution. So this says that phi is constant along a second set of Mach lines with a negative slope. In the previous case, the Mach lines had a positive slope. Now we have negative slope. So they have a slope of minus of 1 over lambda rather than plus of 1 over lambda. So what does it mean? If you plot those lines, they will show up as shown in here. Those would be the red lines that we have shown in here. So we have on the upper side of the airfoil one solution. On the lower side of the airfoil we have another solution. These solutions are discontinuous. We don't need to worry about communication between the upper and lower surface because sound waves cannot travel against the free stream. They are traveling too slowly compared to free stream. Therefore, they cannot go around the leading edge and influence what's happening on the bottom surface. Likewise, whatever is happening on the bottom surface cannot travel downstream, swim upstream, and affect the upper surface. Therefore, the upper surface and lower surface has discontinuous solutions, discontinuous velocities, discontinuous pressure. But we don't need to worry about it. Kutta condition is satisfied at the trailing edge by the formation of shock waves and expansion waves. But we are only interested in what's happening on the airfoil. We don't need to worry about the Kutta condition or what happens downstream of those shock waves or expansion waves. Now let's apply the boundary condition on the lower surface, for example. d phi dx and d phi dy should be, this is this body slope. So d phi dy will be dg d eta times d eta dy. D eta dy is lambda. Therefore, we get d phi dy equal to lambda times dg d eta. Plug it in here, then we get dg d eta equal to this expression. Now let's go to the surface pressure. Again, on the lower side, we need an x derivative of phi. So here is phi. Take an x derivative. Again, by chain rule, it's dg d eta times d eta dx. D eta dx is 1. Therefore, d phi dx is just dg d eta. So Cp becomes minus 2 times dg d eta divided by V infinity. From the previous slide, we had this expression. So plug it in here for d phi dx. V infinity will cancel out because there's some V infinity up here. Then you just get this expression. So basically, on the lower surface, the pressure coefficient is a function of the local body slope multiplied by negative of 2 over lambda. How about on the upper surface? We get a very similar expression. You get plus of 2 over lambda times du by dx of the upper surface. So we only need to know the local surface slope to compute the Cp. We don't need a coupled system of equations like the vortex lattice equations we've been talking about in the past, or along the span like Prandtl did in 3D finite ring theory. In supersonic 2D potential flow, upper surface can be completely found based on the upper surface body slope. Lower surface information can be found completely based on the lower surface body slope. Now we can integrate the CL. All we'll have to do is plug in the pressure coefficients for the lower surface, pressure coefficient for the upper surface, integrate it. This is a very simple integral, dy dx times dx. So it will become y leading edge, my y leading edge minus y trailing edge, because there's a minus here. Same way here. So when you integrate it, basically we will get y trailing edge minus y leading edge by quad. You notice that when you put a 1, you're talking about a y trailing edge. 0 means y leading edge. So you get a CL equal to plus 4 times alpha divided by square root of m infinity squared minus 1. So CL is only a function of alpha. Camber does not show up anywhere. So camber does not affect the lift. It only affects the drag. That's why supersonic aircraft such as F-15, F-22, F-18, F-35, the wing has 0 camber. Sometimes you need a small amount of camber in subsonic flight. So for example, if you look at Concorde, during the takeoff, they will drop the leading edge flat, they will drop a trailing edge flat to camber the airfoil so that they can take off. But once you go to supersonic flow, camber does you no good. It does not affect your lift at all. It only affects your drag. So we could do the same thing. This is the expression for the CL that we just developed. Let's put it on the right side. This is the supersonic regime. This is the rule that we just developed. This is called the Ackeret's rule. This is the Prandtl-Glavert rule. This is the nonlinear rise in lift we talked about. This is the shock-induced stall. Here the lift recovery occurs when the shock moves to trailing edge. Then it follows the Ackeret's rule. So Prandtl-Glavert rule to the left side, Ackeret rule to the right side. And this is the transonic regime where everything is completely nonlinear. Therefore, this curve combines the Prandtl-Glavert rule and Ackeret's rule together. You could likewise compute the drag. The easiest way is to compute, put Cp upper times the upper surface slope. The higher the slope, higher the drag, because we are now looking at the projected area in the x direction, which is delta y. So when you do the integration, you get the slope squared. The more the camber you have, the larger the slope of the body. The more the alpha you have, the larger the slope of the body. The more the thickness you have, the larger the slope of the body. So camber, thickness, camber quadratically affect the drag. If you double the thickness, drag is going to go up 4 times. If you triple the thickness, drag is to go up 9 times. So thinner the body, the better in supersonic flow. So now we can do an example. Let's take a flat plate at an angle of attack. Flat plate is a straight line. Therefore, the only slope you're going to get is the slope of the straight line, which is minus alpha. So the airfoil is going from this way. So it's got a straight line with a negative slope of alpha. So if you put a lift coefficient, it'll be, this is the lift coefficient. Drag will be, because the slope is a constant, when you plug it in here, this is a constant, alpha, minus alpha. When you square it, alpha squared, 2 alpha squared will come out of the integral. So you'll get 4 alpha squared over square root of m infinity squared minus 1. So if you double the angle of attack, the drag will quadruple. If you triple the angle of attack, you'll get the drag that is 9 times higher. So you don't want to disturb the flow a lot. In supersonic flow, you want to just enough to produce lift, but not enough to produce a lot of drag. So we could do a little bit of algebra. We could think of the upper surface as made of a thickness, camber, angle of attack. So linearly superpose the camber, thickness, angle of attack. Now when you do the dy dx, it'll be the slope due to the camber, slope due to the thickness, and slope due to the alpha. Now we could square the upper surface slope, lower surface slope, add them together, integrate it. So if you do a little bit of work, thickness, camber, and angle of attack, add them together, compute the slope, square it, add it, then you're going to get basically an angle of attack effect, thickness effect, and camber effect. So if you double the thickness, you get to quadruple the drag. If you double the camber, you get quadruple the drag. That's why supersonic aircraft such as F-15, F-22, F-35, Concorde, they tend to have as little thickness as possible, as little camber as possible. That means you don't store the fuel inside the wing, you store the fuel inside the fuselage. You don't store the landing gear or anything inside the wing. You don't put anything like a supporting system for actuators, for flaps, slats, because anything you increase the thickness is going to quadruple your drag, so you want to avoid it. So in summary, in linearized supersonic potential flow, we have simple expressions for lift, pressure coefficient on upper, lower surface, analytical expression for alpha, and analytical expression for the drag. So these could be used to look at airfoils. You don't want to have a highly designed cambered airfoil because any camber is going to make it increase the drag. In fact, a flat plate airfoil, the thinner the better from a drag perspective, also from the lift perspective, because camber doesn't do an ounce of good for us. It only messes up things in terms of drag. So we're going to stop at this point, and in our next recording, we will show some solutions, analytical problems, and show you how this works.